Okay, welcome everyone. Any questions before we get started today? So I want to point out that there is a nice book available for free online. I have a link to it in the syllabus for this course. It's called Ratner's Theorem and on unipotent flows, and it's a really good reference for a lot of details about Ratner's theorem. Our discussion is going to be sort of more impressionistic than what you will find in this book. So I wanted to point out that reference to you. And I thought I would start today by let me just say what my program is. I want to review some stuff about hyperbolic space. So talk a little bit about H2 itself, some more of its geometry, and then move on to a discussion of lattices in general, and then on to a discussion of the Oppenheim conjecture in the context of these lattices, and then describe what this has to do with Ratner's theorem, how Ratner's theorem gave rise to this, and also clarify the connection between Ratner's theorem and Hyperbolic's theorem. Okay, so let me start by saying something about H2, which I've said informally several times, but which deserves to be stated as a theorem. So here's a theorem that shows that hyperbolic space is very different from H2, from Euclidean space. So it says for any compact region, by which I mean say an open set with smooth boundary. This is just for convenience, with smooth boundary, omega contained in H2, we have that the area of omega is less than or equal to the length of the boundary of omega. And this explains a lot, because you see whenever you have if you were to take a ball, then the boundary of the ball and the ball are interrelated by this inequality. In fact, you have that if you take the ball of radius r and you increase r slightly, then what you add to the ball is a small strip of height delta r, and whose length is the length of the boundary of the ball. And so here we have the area of the ball, and here we have the length of the boundary. And what this inequality is telling us is that the rate of change of the area of the boundary of the ball, this is actually equal to, that is the derivative of this with respect to r, so I'll put a dot there for the rate of change, is equal to the length of the boundary of the ball. But the length of the boundary by this inequality is greater than or equal to the area. So in other words, the area, roughly speaking, has the property that A dot is greater than or equal to A. Now, if we were to take the exact solutions to A dot equals A, then the solutions would be e to the r. So if A dot were equal to A, the area would grow like a constant times e to the r. Since the area is greater than or equal to A, it grows at least exponentially. A dot is greater than or equal to A, it grows at least exponentially fast. And so this theorem captures one of the mechanisms of exponential growth in the hyperbolic plane. So let me prove it. The proof is very easy in the upper half space model. So we'll use the model where H2 is, let's say, contained in the complex plane, and the hyperbolic metric is the Euclidean metric divided by y. Y is the imaginary part of z, x is the real part of z. And there's many inequalities of this type, and the way you prove them is by Stokes' theorem. What you try to show is that the area is, which is given by a 2 form here, is the differential of a 1 form, and that 1 form can be chosen to be bounded. So if that 1 form is bounded, then the integral of the 1 form over the boundary is controlled by the length, and it in turn controls the area by Stokes' theorems. So in the case of the hyperbolic plane, we can make that very precise. So we let alpha be, let's say, x dy over y. Sorry, I'm saying this wrong. Hang on a sec. Yeah, sorry. What I meant to say was let alpha be dx over y. Then we can observe 2 things. So remember, alpha is something you can plug in and apply to a vector. So the absolute value of alpha applied to a vector is bounded by the Euclidean length of its vector. In fact, it's bounded by the x component of its Euclidean length divided by y. But that in turn is bounded by rho. So the absolute value of alpha applied to a vector is less than or equal to rho applied to the vector. So we say the absolute value of this 1 form is bounded by the metric. But d alpha is what? Well, by let's just differentiate. The only function here is y. You get minus 1 over y squared. But then dy dx, reversing the roles of y and x, you get dx dy over y squared. And so the absolute value of d alpha is exactly equal to the absolute value of the area form on your surface. Okay, so we found a 1 form whose size is bounded by 1, and its exterior derivative gives the area form on the hyperbolic surface. And so if the area of omega is just equal to the integral over omega of d alpha, but that's equal to, by Stokes' theorem, the integral over the boundary of omega of alpha itself. And because of this inequality, that's less than or equal to the integral over the boundary of omega of rho itself. And that's equal to the length of the boundary of omega. Okay, so this is a fairly precise isoparametric inequality that's much better than what you would have in Euclidean space. In Euclidean space, you would have something about relating the area and the length of the boundary squared, right? So, and it's optimized in the case of a circle. You have pi r squared here, 2 pi r here, and so that you square this and divide by 4, that's an upper bound for the area in Euclidean space. So notice that this is not length squared. This inequality is not homogeneous in units of length. If you were to change your metric by a constant factor, these 2 sides scale in different ways. But that's because there is a natural unit of length in hyperbolic space because of the fact that we have constant curvature -1. If you scale the length, the metric rho, the curvature changes. So that's built in to the fact that we're able to compare length and area here. The second thing I want you to notice is why does this argument not work in Euclidean space? So in Euclidean space, what could we try to do? So in R2, we could set alpha equal to x dy. And then things would look pretty good. D alpha is dx dy. Okay, but now you see, now we have the problem that this one form is unbounded in the Euclidean metric because of the factor of x in front of the dy, whereas this one form is bounded in the hyperbolic metric. So that's sort of the fundamental difference between these two spaces. Okay, so this explains in a sort of qualitative and yet rather sharp quantitative way why balls and spheres grow at an exponential rate in hyperbolic space. At the same time, it should be intuitively clear to you that balls and must grow exponentially in volume for the following reason. We know that there are tilings of hyperbolic space corresponding to the free group. So a picture that we've looked at before many times, just as an example, is if you take an ideal quadrilateral and start reflecting through its sides, you get a beautiful tiling of hyperbolic space. And if you identify opposite sides, then you get, as a quotient hyperbolic surface, a torus. And on this torus, we can draw a spine for the fundamental group. And what is the fundamental group? It's the free group on two generators. I've drawn two loops representing the two generators of the fundamental group. And the edges that I've drawn have bounded length. So when I take the pre-image of these two loops up here, I get an embedding of the Cayley graph into hyperbolic space. Now, it's clear combinatorially that in the free group, if we were to take the graph of the free group, the Cayley graph, and make the edges have length 1, then the vertices at a given distance from the origin grow exponentially fast. So the number of vertices at distance d, let's call that dd, what does it look like? So for d equals 0, there's 1. For d equals 1, there's 4. But then after that, each vertex gives birth to 3 new ones. So after this, it's 3 times 4, 3 squared times 4, and so on. So the number of vertices at distance d from the origin in this Cayley graph, itself being sort of a trifurcating tree, grows exponentially fast. On the other hand, we could replace this dot by a ball of some definite radius with positive area. And the balls, provided this ball is embedded in X, upstairs we get disjoint balls around each vertex of the Cayley graph. And so we get 3 to the d times 4 embedded balls of definite radius within a definite a distance roughly d of the origin. So since the number of points in the Cayley graph grows exponentially fast, the area of the ball of radius r in hyperbolic space has to grow exponentially fast to accommodate this tree. And in fact, there's a famous quote from Darwin, and I think it's also essentially the subject of Malthus's thesis, that essentially says a tree doesn't embed in the Euclidean plane. In other words, given enough resources, populations grow exponentially fast, but we don't have exponential growth of area or resources on the Earth. The Earth is actually even positively curved. And as a result, if you try to do this embedding, you get enormous competition at the boundary of the trees, and that's the source of the driving force of natural selection in Darwin's words, which are quoted. They're very beautifully written. They're quoted in my course notes. Okay, so I want to go back to this fact, which I hope people internalize as part of their geometric image of hyperbolic space, and ask you to, as just a quick breakout room thing, to do an exercise. And the exercise is, in the spirit of this exercise, it's nice to have this intuitive feeling that things grow exponentially fast, but where do exact formulas come from? How hard are they to derive? So the problem I want to pose is to calculate the length of a circle of radius r in hyperbolic 2 space. Now, of course, I know you can find the answer, and feel free, if you wish, to look it up on Wikipedia. But the challenge is to find a nice proof of this, or figure it out, or take facts that you already have at hand and try to use them to get the answer to this problem. This is an exercise that we should all know the answer to, and there's various ways of approaching it. And so let's just break out briefly into breakout rooms for, I don't know, 6 minutes, and calculate what the length is of a circle of radius r. Okay. So let's see. Let me try. Okay. So please go ahead and join your breakout room. Okay, welcome back. So who would like to report on their research? Somebody from each breakout room, raise your hand, please. Okay. Sorry, I don't have my gallery view on. So if you could raise your hand in the participant window, that would be easier. Yes, Jonathan.
It's not quite a full solution yet, but we were trying to work in the disk model.
Okay.
And we were we were in the middle of expressing the radius, the actual radius in terms of what the radius looks like the hyperbolic radius in terms of what the Euclidean radius is in the disk model.
Okay, so you worked in the disk model with the metric 2 dz over 1 minus the absolute value of z squared. And let me see if I understand your method. What you were going to do is first write down the length of the circumference in the hyperbolic metric of a circle whose Euclidean radiuses are. And what did that come out to be?
I think just like 2 pi times the metric.
Right. So on the circle of radius r, so it would be 2 pi times 2, which would give a 4 pi over 1 minus r squared. Great. And then what you have to do is also figure out s, which is the length of the radius of this circle. So s is some function of r, which you can get by integrating from 0 to r, the metric. And then you can solve for s in terms of r, plug back in here and get the answer. Okay, great. I will confess that this is the method I have used myself perhaps 10, 15 times. Can never remember what the answer is. Anybody else want to report on their research? Yes, Rohil.
Oh, well, we used the same method, so I don't know if I have anything new to add.
Well, did you get to a final result?
No. I think similar stage, converting to the actual hyperbolic distance.
Okay. By the way, you're free to use Mathematica in these calculations. Anybody else want to report? Ben?
Oh yeah, so we also talked about like the method you said, and I think there might be another way to do it. Like if you know, like since it's constant curvature -1, you know the Jacobi field satisfy the ODE like y double prime is equal to y, which I think you should get like hyperbolic sine or something. And then knowing like just the differential of like the exponential map will like give you the Jacobi fields.
Okay, interesting. So another method is to somehow use Jacobi fields. I think there was one more breakout room. Does somebody else want to report? Yeah, Yanchuan.
Well, we use the same, like the unit disk method. I just got to the place where I know how the two radius are related, but not much further.
Oh, great. Okay, so you solved how s is this function f of r.
Right, yeah.
And what did you get?
I think it's, which one is r? The r is the Euclidean?
R is the Euclidean and s is the hyperbolic.
It's log 1 plus r over 1 minus r, or something like that. I just erased that. Oh no.
Right, something like that. Okay.
Yeah.
Okay, so that's great. And all of these methods will work and can be pushed through. But what I'd like to present to you is another method. And it's interesting because you can use this method I'm about to present and these calculations to argue about what is the real model of hyperbolic space. Is it the disk model? Is it the upper half plane model? Is it the Minkowski model? So to illustrate a different approach, let me solve the same problem on the sphere. Okay, so we have constant curvature plus 1, what is the length of the circle of radius r? So what you can do is you can embed the 2 sphere in R3 as the unit sphere and put the center of your circle at the North Pole. And then we know very well how to parameterize a geodesic going down towards the equator. After you've gone distance r, which is just this angle here, the x value has gone up to sine r, and the y value has descended to cosine r. So that means that this distance here is sine r. But now the beautiful fact is, since you're in R3, which is a flat space, this circle lies in a plane where we can use the Euclidean metric. And so once we know the radius of this circle in that Euclidean plane, then we know the length of the circle. So it's actually a flat circle when you look at it in the ambient space. In the ambient space, though, its radius is not r, its radius is sine of r. So the answer is that the length of the circle of radius r is 2 pi sine r. And this is obtained by just finding this Euclidean circle that has, finding your circle on the sphere and then thinking of it as a Euclidean circle, because it is, after all, a planar slice of the sphere. And by the way, you can also quickly calculate then the area of this polar cap, because as I mentioned, the area is always the integral of the length of the circle, dr. So the integral of sine from 0 to r is 1 minus cosine r. Now, if you look in some books, you'll see this it represented in terms of something like sine squared r over 2. That's just using a trigonometric identity. But in some ways, this is even a more natural way to present it, because then it's obvious that the derivative of area is length. And you'll notice that once you guess it's going to involve sine, this is really the only formula you can write down, because it has to be asymptotic to 2 by r for r small. Okay, so once you see what happens for the sphere, it's pretty easy to guess what happens for hyperbolic space. Namely, in hyperbolic space, sine should be replaced by sinh r. And cosine should be replaced by cosh. But of course, the integral of sinh is cosh, not minus cos. So this becomes cosh r minus 1 in the hyperbolic case. And in fact, the proof is the same. It's just that we need to use the hyperboloid picture of hyperbolic space as a sphere in Minkowski space rather than the positively curved picture in ordinary Euclidean space. So we work in R21 with our metric being dx squared plus dy squared minus dt squared. And we take our origin to be the south pole of the hyperbolic plane, if you like. This is the hyperboloid, which consists of the vectors such that v squared equals minus 1. And again, we know very well how to parameterize a unit speed path along the hyperboloid. If we want to just change the x coordinate, keep y equal to 0, remember the xy plane is down here, then this becomes sinh of s and cosh 0, and then cosh of s. And we know we're on the hyperboloid because sinh squared s minus cosh squared s equals minus 1, as it should. Okay, and now we use exactly the same fact, which is that in R21, the metric restricted to the xy plane is nothing but the Euclidean metric. And the circle of interest is this one here, which is simply the intersection of the hyperboloid with the XY plane translated to height cosh s. So this is just the circle at height t equals cosh s. And what's its radius? That's the value of x here. It's the sinh of s. So we're reduced to calculating the length of a Euclidean circle of radius sinh s, which gives us 2 pi sinh r. Okay, so given that this doesn't involve integration, logarithms, etc., but it's just something you can see once you know how to parameterize a geodesic in the Minkowski model, I think this kind of advocates for the Minkowski model as one of the better, if not the primary model for thinking about the hyperbolic plane. On the other hand, you see, why do we work in the disk and the hyperbolic and the upper half plane? It's because we've been taught that we should work intrinsically as much as possible. But in fact, there's a lot to be gained by working extrinsically, particularly when your space, the ambient space in which you're working is flat. It can help you a lot in understanding a negatively curved subsurface. Okay, so so let me move on to the study of lattices, for which this calculation and similar ones will not be irrelevant. Okay, so this is topic 2, lattices. And so for lattices, here's what I want to discuss. So what is a lattice? It's a discrete subgroup isomorphic to Zn sitting inside of Rn. So it does not lie in any subplane. It contains a basis for Rn. So how can you describe a lattice? Well, for first thing is there's an invariant. There's the determinant of the lattice, or at least the determinant if it's oriented, or if you like, the volume or co-volume of the lattice, which is the volume of the quotient space Rn mod A. And it's convenient when you're studying lattices to scale them so they all have co-volume 1. So if this is equal to 1, which we can achieve by normalization, then we say lambda is unimodular. And also, we can associate to a lattice the torus here. So we have a geometric picture of a lattice. In fact, it gives us a compact quotient group. And finally, if we were to look at the lattices in the case n equals 2, then it's familiar to us that the set of lattices up to scale, which can be regarded as the set of unimodular lattices, is equal to the quotient of the upper half plane by SL2Z. It's our friend, the modular surface. And so we have a good picture of what the space of all lattices looks like in dimension 2. Now, I should say that here, when are we identifying two lattices? We're identifying two lattices if they differ by rotation, that is, by an orientation preserving automorphism of R2. And if we wanted to take the raw lattice itself, not the lattice up to rotation, then what we would put here is SL2Z backslash SL2R. In other words, we look at the homogeneous space, gamma mod G, rather than the space, the corresponding surface. Doesn't make too much difference. We're now just have a circle's worth of lattice over each point on the modular surface. And in general, for general n, we would have that the set of lattices, let me call it Ln, the unimodular lattices in Rn, can be regarded as the quotient space SLNZ modulo SLNR. Now there's a little nuance here, which is that the way we normally identify lattices with the upper half plane is not unimodular. So usually if we take H and tau, a tau and H, we associate to this the lattice Z plus Z tau, which is distinguished by the fact that it has one vector of length 1, a standard vector of length 1, and then this other independent vector of length tau. And what we see here is that the area, the co-area of this, is equal to the base times the height, so it's equal to y. In other words, it's equal to the imaginary part of tau. So if we want to associate to a point in the upper half plane a unimodular lattice, we should rescale by the square root of tau. So it should really be z times 1 over the square root of y plus z times tau over the square root of y. So in other words, you might have lattices that appear to be collapsing in the upper half plane because tau is going to 0. But in fact, the lattices are all staying the same. And indeed, if you change the value of tau by a Mobius transformation, SL2Z, this lattice will not change except possibly by a rotation. Okay, so now we have the following question. What we notice is that the modular surface is not compact. The space of lattices, even once you've normalized so they have area 1, is not compact. The space of tori, normalized so they have area 1, is not compact. Tori and lattices can collapse. For example, you can take the lattice generated by a vector of some large length L and an independent vector of small length 1 over L. That's a unimodular lattice, and it degenerates since the length of its shortest vector goes to 1. So the question that we can ask is, when is a set of lattices compact? When can we choose a convergent subsequence from a space of lattices? And another way we can think of this in terms of our friend the modular surface is that if we have a sequence of points tau in the upper half plane, they give us a sequence of points tau n down on the modular surface. And these points tau n might go out the cusp, in which case they leave every compact set in the space of lattices. So we want to be able to recognize, given a sequence of points in the upper half plane, when downstairs they're going towards the cusp. Well, this question has a beautiful answer and a very simple one that works in all dimensions. This is called Mullers compactness criterion. So what we notice is that if we have a lattice in Rn, there is a natural invariant associated to it, which is the length of its shortest vector. So our definition is we let M of L be the inf over lambda and L star of the length of lambda. So L star, sorry, I should have called this lambda. The length of the shortest vector, where lambda star is lambda minus the identity. And what you'll notice is that this M lambda is also measuring the length of the shortest geodesic on the quotient torus. Or it's measuring the injectivity radius of the torus, because the length of the shortest geodesic controls the it controls the radius of the largest embedded ball about the origin, which by homogeneity is the same as the radius of the largest embedded ball at any point. And of course, for any particular lattice, this is positive. And Mullers theorem says that the set of lattices lambda in this space I called Ln over here, such that the length of the shortest lattice element is bigger than some r greater than 0 is compact. And moreover, these compact sets determined by each r, they exhaust the space of lattices. So a fancier way to put it is that M from the space of lattices to the real line with the origin removed to 0 infinity is proper. That is, the preimage of any compact set is compact. So since M is continuous, if you have a compact subset of the space of lattices, M is bounded below on that compact subset. And conversely, if M is bounded below, then you're in a compact subset. So this quantity, the length of the shortest lattice element, the length of the shortest geodesic on the torus, characterizes compact subsets of this moduli space of lattices, or this moduli space of tori. Now that still doesn't quite, I mean, that answers in principle this business about how do you tell when you're going to infinity in the upper half plane. It says it's when the length of the shortest lattice element in this normalized lattice is going to 0. But that's a little bit implicit, and there's maybe a better way to say this, which is the following. So a picture for, let's look at the picture for n equals 2 of the locus where m of lambda is greater than or equal to some constant r naught. Okay, so let's think about what happens when we're to an ordinary lattice when we're in the upper half plane. If we want to look at the length of a given element of a lattice, let's move back to this picture here. Another way to say this, by the way, would be to say m of lambda is the inf over lambda star of the length of lambda, and then we could divide by the square root of the area. And that way we wouldn't have to worry about whether our lattice is unimodular or not. Let's think about what this picture looks like in the upper half plane. What does the locus where m lambda is bigger than r naught look like? Well, for every pair of integers a and b, we have a lattice element, a plus b tau. And so what we want to look at is the locus where a plus b tau divided by the area, which is the imaginary part of tau, to the 1/2 is less than or equal to a given constant. And it turns out that, so for actually every pair of rational numbers, a over b, we get a potential shortest vector and then a locus in the upper half plane where that particular vector is short. So, so for example, suppose we let b equal 0, then we would just be asking, and so we can also reduce to the case where the GCD of a and b is 1, because the shortest vector will always be a primitive vector. So for example, if a is 1 and b is 0, this is just 1 over the imaginary part of tau. So the region where some particular vector coded by 1, 0 is short is just the locus where the imaginary part of tau is less than a constant, or equivalently, the locus where you're above a given line in the upper half plane. And indeed, if tau is up here, anywhere up here, then and the height of this line is large, then the unit vector that we're using to generate this lattice is in fact the shortest vector in the lattice. And it's very short compared to the area when the imaginary part of tau is large. So this is a typical subset of the locus where m of lambda is greater than or equal to r naught. And what we can see is that it's a horoball resting on infinity, a horoball centered at infinity. On the other hand, we notice that this locus is SL2Z invariant. Length of the shortest vector doesn't depend on the choice of any basis vector for the lattice. And so the orbit of this horoball under the action of SL2Z also gives us, has to be excluded to create this compact set. And if you compute what this locus looks like for other values of A and B, what you'll find is that resting on the point A over B, there's a horoball, and the radius is equal to a constant over B squared, where this constant is related to the R naught here. So in other words, the space of thick lattices in the upper half plane is obtained by excluding a horoball that rests on one horoball for every rational number. And the radius of that horoball is proportional to the one of the denominator squared, and the constant you put in the numerator there depends on what this R naught is. So this is what the locus where m of lambda looks like upstairs in the cover of the upper half plane. And when you project downstairs, this just gives this a standard horoball neighborhood of the cusp. Okay, so Mullers theorem then says that if you take a sequence tau n, which never enters any of these horoballs, then when you map it down to the quotient space, it stays in a compact subset, which means that you can apply elements of SL2Z and then pass to a subsequence so that it has a limit. So that's a pretty powerful technique for extracting limits of lattices. Okay, so now why is it true? Why is Muller's criterion true? So let me first give the proof for n equals 2. So suppose we have a lattice, lambda contained in R2, the co-area is 1, and m of lambda is greater than or equal to r. So then what we do is we choose a basis for lambda. As follows. So first, we let E1 in lambda star, we take this to be the shortest vector. Okay, so let me draw that as if it's horizontal. It doesn't have to be horizontal, but on the other hand, it's a inconsequential change to rotate the lattice by a constant. So once we have this shortest vector, then we have within the lattice the subgroup CV1 that it generates. And now, to get a basis for the whole lattice, I let E2 be the shortest vector in the complement of the subgroup I've already generated by E1. So, so E2 will lie somewhere, and what we can say is the following: we would never take E2 to be way over here, for example, because if we chose this vector as E2, we could translate by E1 to make it shorter. And in fact, you could always make it shorter until its projection to the vector E1 is less than or equal to half the length of E1, although it might be going in the minus direction as well. So E2, once chosen to be the shortest vector, lies in this strip orthogonal to E1, whose width is equal to the length of E1. Okay, so let me change to a color so we don't completely lose this to the background text. So our second vector, E2, is here. Now notice that the vector E1 is not too short because of this criterion here. So R is less than or equal to the length of E1, and of course it's also less than or equal to the length of E2. But what can we say about the size of E2? Well, remember that the area of the lattice is equal to 1. The co-area is equal to 1. So the height of E2 times the length of E1 is equal to 1. And therefore, on the other hand, the length of the height of E2 plus the length of E1 is an upper bound for the length of E2. So what we find is that the length of E2 is less than or equal to another constant, big R, which depends only on little r. So in fact, what we see here is that if the length of E1 were actually equal to R, then the E2 would have to lie, its height would have to be between plus 1 over R and minus 1 over R. And so its length would be at most R plus 1 over R. So here we could take this to be R plus 1 over R. Okay, and now we're done, because if we have a sequence of lattices with a basis E1 and E2, such that their co-area is equal to 1, then if these vectors are bounded above and below, we can pass to a subsequence such that those basis elements converge. And then in the limit, we can just take the lattice generated by those basis elements. So since this region here is compact in R2 cross R2, we get a compact set of lattices. Now you might worry a little bit, how do you know that in the limit, E1 and E2 generate a discrete set? How do you know, for example, that they remain linearly independent? But remember that all along, these are unimodular lattices. So the cross product, or the determinant in E1 cross E2, is in absolute value equal to 1 for all of these pairs. And so in the limit, that cross product is also non-zero, and therefore these limiting vectors are linearly independent. Okay, so that's the proof of Mullers compactness criterion. And again, there should be an intuition that goes behind this, which makes the theorem seem almost obvious. So the geometric theorem is that if you have a sequence of tori, and the total area of the torus is 1, if you have a sequence of tori of area 1, and the injectivity radius of this torus is bounded below by R, so at every point there's an embeddable of radius R, then there's no way for these tori to degenerate. In particular, the diameter is bounded below by some function of r. So they can't get too big, and they can't collapse because of this lower bound on the injectivity radius, and therefore they have a convergent subsequence. And so there's this sort of various softer notions of convergence of spaces as opposed to convergence of lattices. And those softer arguments could be applied to show directly that these tori converge in some geometric sense. So for example, why is the diameter bounded? Well, if you have 2 points, you can join them by a chain of balls which overlap at most twice, and then each of these balls can be chosen to be of radius r. So the number of balls is bounded in terms of the area of T, which is 1. And therefore, the number of balls it takes to get from the origin to any other point is uniformly bounded above. Okay, so I allude to this geometric picture because there's a very similar sounding theorem about the space of hyperbolic surfaces. And its proof is not so easy to give using this chain of ideas, but it's quite easy to give using this picture. So this is called Mullers Theorem. And it says for each r greater than 0, mg of r, which is the set of hyperbolic surfaces of genus G, such that the length of the shortest geodesic on X is greater than or equal to r, is compact in the moduli space of Riemann surfaces of genus G. And of course, here G is greater than or equal to 2. So in other words, the only way a hyperbolic surface can degenerate is by the length of some geodesic going to 0. So just as a small remark, you'll notice that we had to normalize here so that the area was equal to 1. Here we've normalized so that the curvature is equal to -1, which then forces by Gauss-Bonnet the area to be equal to 2 pi times the Euler characteristic, which is 2g minus 2. So in a fixed genus, the area has already been normalized, and then a lower bound on the injectivity radius gives the desired limits. And indeed, this theorem of Mumford's has nothing to do with dimension 2, just as this theorem about lattices has nothing to do with dimension 2, although I gave the proof in that case. This theorem can be generalized to show that if you have a sequence of n-dimensional hyperbolic manifolds, and they're compact, then they have a convergent subsequence provided their volumes are bounded above and their injectivity radius is bounded below. Okay, so this compactness criterion is one of the motivations one should have in mind when studying lattices, quadratic forms, and it's important in the theory of Diophantine approximation, and it's important when we consider, when we get to the Oppenheim conjecture. Okay. So let me give you an application of Mullers criterion. So there's a theorem that you probably have heard of and seen proved in a number theory course, which is actually very geometric. And it's called the Dirichlet unit theorem. Raise your hand if you've heard of the Dirichlet unit theorem, even if you might not be able to state it. Raise your hand high. Don't worry, I'm not going to call on you. Okay, so some people haven't heard of the Dirichlet unit theorem, although maybe when I state it, you'll recognize it. So let me say what this theorem concerns. So when one studies an algebraic number field, there are two things that are of great importance. One is the ring of algebraic integers, and the other is the units in the ring of algebraic integers. That is the invertible elements. So if K is a finite extension of Q, then inside of K, we have this beautiful lattice. This is the ring of algebraic integers. And then inside of the ring of algebraic integers, we have the units. So these are the integers such that x inverse is also an integer. For example, in the ordinary integers, the units are just plus or minus 1. Usually if you take an integer like 7, its reciprocal is not an integer. And these integers are easily recognized because we have the norm map going from K down to Q, which is when restricted to the multiplicative group, it's a homomorphism. The norm of a given element X is the product of its various Galois conjugates, X1 up to XD. And this is equal to 1 on X and O, if and only if X is a unit. So the units are the solution to some sort of equation, the norm equation, that happen to be integers in the field. And of course, this is obviously a unit because the remaining product here, x2 up to xd, that's also a sequence of algebraic integers, and it clearly forms an inverse to x1. Okay, so what happens in particular cases? Well, let's do the case of quadratic fields. So if K is Q adjoining the square root of minus D, where D is positive, if it's a quadratic imaginary field, then O check is a finite group. In fact, we can always think of a quadratic imaginary field as sitting inside of the complex numbers. And then the units, the norm corresponds to Z times Z bar. So the norm is the ordinary Euclidean norm on the complex numbers. And so we're looking for elements of our field, Z plus Z square root of minus D, or a Z mod 2 extension of that. This is approximately the ring of integers up to finite index. We're looking for elements here which happen to lie on the unit circle. And in fact, there are very few algebraic integers that lie on the unit circle at all, at least those that are of degree 2 over the rational numbers. And to see that, it's useful to use another invariant, which is the trace. So remember, the trace of an element of the field is the sum of its Galois conjugates. And again, if X is in O, then this is in Z. And so if you had an algebraic integer on the unit circle, in a quadratic imaginary field, its trace would just be twice its real part. And so if you have a unit on the circle, the trace of X would have to be plus or minus 1, 0, or plus or minus 2. And those correspond to the cube roots, the sixth roots of unity. So the cube root of unity, its square, minus its square. Anyway, they correspond to the solutions to those equations, correspond to the points we know well. There's I and minus I. There's plus or minus 1. And then there's the sixth root of unity, which I'll call omega. And it's the other primitive sixth and cube roots of unity. So in particular, there's only finitely many possibilities. And the reason there's only finitely many possibilities is because the norm of an integer in this kind of field is positive definite. Indeed, the norm of A plus B square root of minus D is just the product of this number times its Galois conjugate, which is a squared plus db squared. And so for this to be equal to 1 gives us a priori bounds on A and B, so certainly the unit group has to be finite. So Dirichlet's unit theorem tells you, more generally, how many units there are in a given field. And what I draw attention to for our considerations is what it says for real quadratic fields and how this is related to lattices. So for k equals q, adjoin the square root of plus d. Be positive now. Now we have that the norm of a plus b squared of d is a squared minus db squared. And we're looking for integral solutions to this equal to 1. Well, the locus where a squared minus db squared is equal to 1, that's is a hyperbola. So we're looking for points which in appropriate coordinates lie on a hyperbola like this. Actually, we could put plus or minus 1 here. Should have done that earlier. And we have infinitely many chances to find integral points. And indeed, the elements of norm 1 form a group because the product of two algebraic integers is again in algebraic integers and the norm is preserved. So what Dirichlet's theorem says in the case of a real quadratic field is that in fact there are lots of units, and up to plus or minus 1, the group of units is cyclic. So this is the Dirichlet's theorem is that the group of units across, and let's mod out by plus or minus 1 the obvious units in a real quadratic field is cyclic. Okay. Okay, so let me try to explain how you can prove this theorem just using the theory of lattices. And in fact, what we'll prove is that there's lots of solutions to this equation. So the proof goes like this. We consider the quadratic form on R2 given by a Q of AB is equal to what I just wrote down, a squared minus db squared. Now the symmetries of this quadratic form on R2 look like what? So by this I mean they're a subgroup of SL2R, and they're the subgroup of automorphisms of R2 which preserve the values of this quadratic form. Well, this quadratic form over the real numbers, although it looks initially like a form like this, 1, 0, 0 minus d, it's equivalent up to a change of coordinates to 1, 0, 0 minus 1. It's just a form of signature 1, 1. So this subgroup is conjugate to the subgroup SL11, sitting inside of SL2R. So in other words, this group is the symmetry group of a one-dimensional hyperbolic space. In fact, you can think of this hyperboloid as the Minkowski model for a hyperbolic space in dimension 1. Now, what we're interested in doing is plugging in integers into this quadratic form. So how do we remember the various the integer points for this quadratic form? That comes from the action of the subgroup SL2Z. So we can take this quadratic form and we can change bases on R2 while preserving the integral lattice. And that won't change the set of solutions to this form. And so the study of this form boils down to the study of the image of SOQR2, which I'm going to call H, in the space of lattices G mod gamma. This is SL2R mod SL2Z. But the study of this image is closely related to the study of gamma acting on G mod H. And what is G mod H? H is a particular form of signature 1,1. SOQ is a particular form of signature 1,1. H is its stabilizer. The determinant 1 quadratic forms are a homogeneous space for the action of SL2R. So this is the space of quadratic forms on, this is the space of quadratic forms on R2 of determinant 1. Okay, so to make a long story short, the upshot is that this space, SO11, is isomorphic to it's isomorphic to the group A. It's just the diagonal group sitting inside of SL2R. That corresponds to the quadratic form X times Y. And what we're looking for is the orbit of A, or the image of A, in G mod gamma. So we want to look at the space of lattices that we get under the action of A, or under the action of the isometries of this form. And so the claim is that the orbit of H on gamma mod G is compact. In other words, if we take the Z2 lattice and we start applying to it symmetries of this form, SOQR, we get a compact space of lattices. So to prove it's compact, we have to prove it's closed and bounded. And the closedness comes from the following very simple fact. When you look at the space of quadratic forms we're interested in, this form has integral coefficients. When you make an integral change of basis, that is when you apply an element to SL2Z, the forms remain with integral coefficients. The space of quadratic forms with integral coefficients is closed, and therefore this orbit is closed. That has to do with considering the action of gamma on G mod H. But why is it bounded? It's bounded because on the integers, this form is never 0. It's never 0 except at the origin, because the square root of D is irrational. If you plug in an integer here and an integer here, you get a number that's at least 1. And therefore, the length of an integral point in this quadratic form is bounded below. So in other words, the quadratic form, the locus where the quadratic form is less than or equal to 1, defines some sort of region like this, and it contains a neighborhood of the origin. But that means that as we apply symmetries of this quadratic form to the integer lattice, we get a sequence of lattices where the length of the shortest geodesic is bounded below, because the value of Q is bounded below. And so by Mullers theorem, they lie in a compact subset of hyperbolic space. So the upshot is that in the space of lattices, the orbit of this conjugate of A corresponds to a closed geodesic, And the generator of this closed geodesic corresponds to a fundamental unit in the field Q adjoining the square root of minus d. Okay, so I've gone a little bit over, but I'll try to elucidate that connection better next time. And that's the motivation for studying the Oppenheim conjecture, which has to do with similar statements in dimensions 3 or more. Okay.